Welcome back to the lectures on quantum field theory, and this is chapter 4 on discrete symmetries, and this is the first video for this chapter, and hopefully this is just the only one. So again, I'd like to remind you that along with this lecture you should also read one of these books by Michukako, Quantum Field Theory, Mandel Anshaw's Quantum Field Theory, and F. Gross Relativistic Quantum Mechanics and Field Theory. So previously we had continuous symmetries discussed in chapter 3, and those were having continuously varying parameters such as rotations that we discussed, rotational groups that we discussed, and also unitary groups. Now this particular lecture will consider different kind of symmetry, and this will be discrete symmetries, and this will be the parity, charge conjugation, and time reversal symmetries. So before we go to the symmetries, we deal with a quantum number first. What is a quantum number? It's a quantity or a property of particle that is conserved in a particle reaction, whether it's decay, collision, or scattering. There are additive and multiplicative quantum numbers. So an additive quantum number n is one such that if you have a particular quantum number, say n1, n2, ni, and that's before reaction, and if you have a different quantum numbers after the reaction, then the sum will just be the same, even though they are not they're not the same initially and at the final state. So the sum should be the same for any reaction. There are also multiplicative quantum numbers such that if you have quantum numbers in its initial state, or for example before collision or scattering or decay, then the multiplication of these quantum numbers at the beginning would also be the same in the final state, the product or the multiplication of those quantum numbers. Sorry, this is supposed to be product, not sum. So anyway, remember this for the additive quantum numbers and for the multiplicative quantum numbers. By the way, I missed something here. This is supposed to be, this one here is supposed to be this. So for a composite system, if a quantum number is multiplicative, then the product of the quantum numbers is the quantum number of the composite system. And also, if a quantum number is conserved, then it represents a symmetry of the system. Now we'll start with the first symmetry, and this is just the parity. So for example, in non-relativistic quantum mechanics, consider a potential V that is symmetric about the origin, and so you will have this one. This implies that if you have a wave function psi x to be a solution of the Schrödinger equation, then this is also a solution together with this. So it solves the equation with the same eigenvalue, because when you look at the Schrödinger equation here, it's just the Schrödinger equation. However, when your potential is has this symmetry, then it's just the Schrödinger equation, still the same. So therefore you can write your this wave function, you can write this wave function in terms of this one here. And so if you transform x to negative x, then your wave function of negative x would also be alpha times your original wave function. So if you do that, you can get the eigenvalue alpha, which is just equal to 1 and negative 1. So this means that you have parity that could be an even parity or an odd parity. So if your wave function would transform like this, then you have an even parity. And if you have a wave function that transforms like this, it should be an odd parity. The parity operator causes the change in sign when x is transformed into negative x in the wave function. In general, it should be space, but in this discussion, it's just one directional, and we just consider the space that's on the x-axis. So you take a wave function and then you apply a parity operator, and this one is the result of that. It's just the psi, but your space becomes negative. Even powers lead to functions with even parity, this one, while odd powers lead to functions with odd parity, and that one. So an even function where your psi negative x is equal to psi x, you have this kind of symmetry. If you flip, in this case, just for this case, if you flip on this axis, you would get the same form of the wave. Flip about this axis here. And for an odd function where this is the behavior, these are monomials with odd powers, say for example x to the first power, x cubed, x to the fifth, and so on. If you flip this this figure here, then the wave function will not coincide with each other, although they are if you flip this this one here about this axis, then this would look like this particular frame, this would look like that, and you would have an even parity wave function. But in this case, it will not coincide with each other wherever axis that you flip, like this for example, or here. and even in this axis it will not. So that's it. That's for anyway. You can just you can be sure of that when you have odd powers. If they are monomials with odd powers, then they are odd functions. And then if you have a function that is just composed of even powers of monomials with even powers, then that is an even function. Applying the parity operator twice in succession gives the original wave function back here. In this particular case, the parity operator can be thought of as a reflection through the y-axis. So parity symmetry in a symmetry, what we call parity, is dealing with space. So it deals with space. So if you invert the space, then you would have that parity going on. So if psi is even, the same function values can be seen. If psi is odd, the negative of the function values comes out. So in either case, another reflection through the y-axis brings back the initial state. So if you operate the parity twice, you will get an identity. The eigenstates of parity are plus minus 1 here. So that's the eigenvalues. I mean, the eigenvalues are 1 plus 1, 1 minus 1, and then you have the eigenstates just the positive or negative of the original one. True reflections preserve the length. If it's just a reflection. Now if your wave function psi is an angular momentum state with angular momentum L, here your state is written this way. If you would review your quantum mechanics, then the parity operator acts on that as this one. Note that alpha here could just be positive or minus 1. So your psi x and psi negative x would have to be solutions of the Schrödinger. Both would have to be solutions of the Schrödinger equation with the same eigenvalue E. In general, if the parity operator and Hamiltonian commute, so if they commute, then parity is conserved. A consequence of this is that a state with parity alpha cannot evolve into a state with parity negative alpha, since the Hamiltonian governs the time evolution of the states. So even parity remains even and odd parity remains odd during time evolution. So if you look at this, if considering a wave function that is non-degenerate eigenstate of H or Hamiltonian with eigenvalue E, then you would have this. But if you have if the Hamiltonian and the parity operator is commutative, then you can also have this. So they're just the same. So the eigenstates of H or Hamiltonian are also eigenstates of the parity operator. Again, earlier, the eigenvalues of P are positive, negative 1, and this rules out states of mixed or indefinite parity. This is a powerful constraint mathematically, and physically it implies that the particles are, or the wave function represents a fermion or a boson. If the eigenvalue of parity is positive 1, then for that particle, or for that wave function that is representing the particle, the parity is even, and if it is negative 1, the particle has odd parity. In quantum field theory, the eigenvalue of parity alpha is a property of particles called the intrinsic parity of that particle. So for fermions, particles with spin 1/2 have positive parity. So an electron and a quark both have alpha equals positive 1, and its antiparticles would have to be negative 1. For bosons, you have the same intrinsic parity for both particles and antiparticles. Parity is a multiplicative quantum number. So let's look at this. So if you have a composite system, so your wave function would be a product of two wave functions composing the system. So say your wave function is this one. So that defines a composite system. If the parities of A and B are PA and PB respectively, then the parity of the composite system is the product of the individual parities that compose the system. So the new parity operators can be constructed by combining P with one of the conserved charges of the standard model. These are electric charge operator Q, and lepton number, and baryon number B. So we know all of these. Baryon number. Going back, these are the things to remember. So for particles with spin 1/2 have positive parity. So an electron and a quark both have parity of positive 1. Remember that electron and quarks have parity of 1. They're antiparticles, that means positron and antiquarks have negative parity. So these are the things that you should remember when dealing with particle interactions. You can check the parities, for example. So when you have a pi particle or pion, so this is composed of a quark and an antiquark. So the parity here is negative 1 in that case, because you have positive 1 and negative 1. So that is the parity of a meson. So anyway, your electric charge operator Q's are just the charges of the particles, and they are additive quantum numbers. Lepton number L are just the number of leptons present in the interaction, and that is supposed to be conserved, and the lepton number in the initial state should be the same in the final state, as well as the baryon number B. These are the number of baryons involved in the interaction. Now, this is a very important note here. Parity is conserved in electromagnetic and strong interaction, but it is violated in weak interaction. So in weak interaction, you have a violation of parity. By the way, there is a labeling of particles. Here you have JP. The J here will just be spin, and P will just be parity. For a spin 0 particle with negative parity, that is pseudoscalar, and they are represented by this JP labeling. So examples of pseudoscalar particles are pi and K meson. So as I've said, they have parities of negative, because they are quarks and anti-quarks. A spin 0 particle with positive parity is called a scalar, and it is labeled this way: spin 0, parity positive 1. An example of a scalar particle is the Higgs Boson, the particle corresponding to the field believed to be responsible for the mass generation of the gauge bosons. Higgs-like particles was detected in 2012 at the Large Hadron Collider. Now, you have a boson with spin 1, and their parity is negative, such as the photon. So it's labeled by this. And you have also a pseudo vector that has a unit spin 1, and its labeling would have to be 1 plus, because it has a positive parity. So again, parity is conserved in electromagnetic and strong interaction. So initially, before the electromagnetic and strong interaction, the parity is supposed to be the same with the final parity of the system. Now, parity is not conserved or violated in the weak interaction. This is proposed by Nobel Prize laureates Li and Yang in the 1950s. This is now called parity violation and can be demonstrated experimentally by observing weak decays of cobalt 60. Parity violation is also apparent in the weak decays of two particles, theta and tau. This one, tau mesons. They're theta meson and tau mesons. They decay in this particular decay. So here you have a meson which is -1 on the left side, and on the right side you have different parities. This one is +1, this one is -1. The final states of these two decays have opposite parity, and therefore theta plus and tau plus were believed to be different particles, but refined measurements show that they're actually the same particle. And at this moment, these particles are now called K plus meson. So the discovery of parity violation in the weak interaction resolved this problem, and today it is called the K plus meson. So let's move on, and we'll be able to see how the violation, how this parity violation is manifested in the weak interaction. Another discrete symmetry is what we call the charge conjugation. Charge conjugation, denoted by C, is an operator which converts particles into antiparticles. Let the state psi represents a particle state, and state psi bar represents an antiparticle state. Then the charge conjugation operator acts as this one here. So it converts your particle into an antiparticle. But if C also acts on an antiparticle, it will convert it to a particle, like here. So it follows also that the C has eigenvalues of 1 plus minus 1, because if you operate two successive charge conjugation, we will go back to the same state psi. And also charge conjugation is a multiplicative quantum number. Now, this is an important note here if you're really serious about particle physics. So charge conjugation converts particles into antiparticles and vice versa. It also reverses the sign of all of its quantum numbers, and also changes the sign of the magnetic moment. That is very important to remember when you do charge conjugation. So everything reverses, all quantum numbers, including the sign of the magnetic moment of the particle. To illustrate that, you have a proton P here, has a baryon number equal to +1 because it's a particle, and the positive charge Q. So QP is the charge operator here, gives you the charge of the proton Q. If the charge conjugation operator is operated on the proton, then your proton becomes an antiproton. And since your QP here equals the charge of the proton times P, your Q of antiproton will give you a -Q. So the charge has been reversed, and then also the baryon number is changed to -1. Everything, all of the quantum numbers supposed to have opposite sign if you do charge conjugation operator. The proton state cannot be an eigenstate of charge conjugation, since the result of this operation is a state with different or opposite quantum numbers. this is also important. The eigenstates of the charge conjugation operator are eigenstates with zero charge neutral particles. So in this particular case, you have a pion. So the pion, the neutral pion, I mean, because you have three pions, pi plus, pi minus, and pi zero. In this case, if you're doing an operation applied to the pion, that is a charge conjugation, and it also gives you the same particle because it's an antiparticle of itself. And so in this particular case, your alpha is equal to positive negative 1. But for a particle called photon, it's a particle of light, the charge conjugation property is a little bit tricky, but we can follow this process here, and we'll be able to get how the charge conjugation goes with production of photons in an interaction. So charge conjugation will reverse the sign of the charge density. So here you have or the current, I mean. So if you apply this charge conjugation on the current density, so it will give you negative J. So now the interaction part of the electromagnetic Lagrangian can be used to determine the charge conjugation properties of the photon. Let's see act on this one. The field A representing the photon, and then you have the current density. So if you apply that, you can actually, this is just an identity. So you can do that. You can put that in between or anywhere in the expression, so that you will have this one here, and this is just equal to J, negative J mu, and this one is of course your conjugation of your field, the field representing the photon, and that can only be invariant when you have this. And if you have a negative A mu there, you'll be able to achieve invariance here. Now, since A mu is the electromagnetic vector potential, so the eigenvalue of charge conjugation for the photon is alpha equals negative 1. So if there are n photons produced in an interaction, the charge conjugation is just equal to negative 1 raised to the number of photons produced or involved in the interaction. So in this case, if you have a neutral pion decaying into two photons, then the two photon state has an alpha equal to negative 1 square, which is positive 1. And in this case, if you apply charge conjugation on the neutral pion, then you will have to get a positive 1 because of this rule, I mean. This rule. So like parity, charge conjugation is conserve in strong and electromagnetic interaction, but not really in electric interaction. And let's look at that in the following sections. Now let's talk about Cp violation. This is the product of charge conjugation and parity. Charge conjugation and parity are each violated in weak interactions. And this led to the hope that the combination of charge conjugation and parity would be conserved in weak interactions. And the answer is yes, almost. Because there is a slight violation that can be seen from the decay of a neutral K meson. The neutral K meson state is a particle which is observed in a linear combination of states with its antiparticle, and interestingly, K0 state or neutral K meson spontaneously transition into its antiparticle and vice versa. So this is the behavior of the K meson. It oscillates into an antiparticle and back to itself. Now your K meson is pseudoscalar, so it has spin 0, and it's, of course, its parity is negative. So if you operate P on K0, it will give you a negative K0, and then for the antiparticle of the K meson, it will also give you a negative eigenvalue. Now let's look at the charge conjugation of K neutral K meson state. So if you do this, it will convert into an antiparticle or an anti-K meson neutral, and of course this one also would be would result. So together you can see from here that Cp together acting on K gives you an antiparticle and with a negative parity, and this one here is also giving you a particle. For an antiparticle, it's giving you an antiparticle with a negative parity, as can be seen from this relation. K0 and anti-K0 are not eigenstates of Cp. So to be able to solve the problem, earlier they constructed states that are eigenstates of Cp out of Ko and Ko bar, or the antiparticle, and check if Cp is still violated. So they constructed a combination of states between K0 and K bar. This one where they call K1 and K2. Normalized combinations of the two of the K meson and the anti-K neutral K meson. If you do vector spaces, then you can also write these two into this one. Now you can see that they are eigenstates of Cp, because it is now K1 and K1 here, and K2 and K2 here. These states can be created in the laboratory. It turns out that K1 and K2 both decay into pi mesons. Now in this case, since you have K1 here and K1 here and K2 here and K2 here, then your Cp is conserved. Is now conserved. So Cp is conserved, then each of these states will decay into a state with the same value of Cp. That is your K1 decays into a state with Cp equals 1, and K2 decays into a state with Cp equals -1. A neutral K meson K can decay into a state with 2 or 3 pi mesons. So the charge conjugation parity eigenvalues of these states are this one. If you produce 2 pi, then Cp is just equal to 1. If there are 3 pi's, then Cp would be -1. If Cp is conserved, then K1 only decays into 2 pi mesons. And if Cp is also conserved, K2 would only decay into 3 pi mesons. But experimentally, this is not the observation. Because it is found that a small fraction of the time, K2 decays in only 2 pi mesons. So there's a slight violation of the Cp, although it's just a very small fraction. Hence, there's a transition from Cp to Cp equals -1 to Cp equals +1. So it turns out that that's a particle called long-lived K meson state, and this is the combination of Kl from K1 and K2. K1 is a combination from K0 bar, and K2 is also a combination of K0 bar, but the Kl is a combination of K1 and K2 with some coefficient or parameter here, epsilon, but this epsilon is found to be very small experimentally. That's just 2.3 times 10 to the -3. So the Cp violation happens, but that violation is very small, and so Cp is supposed to be conserved, but it happens. The violation happens at a small fraction of time. That's what you call Cp violation in weak decay. Now the Cpt theorem. Another symmetry is the time reversal, and we're talking about that restores invariance. This is another discrete transformation on states, turning a state psi into a psi prime that involves with time in negative direction. So in this case, the momentum will change in sign. So the linear momentum becomes -p, and the angular momentum L becomes -L. But all other quantities maintain the same sign. So this is how it transforms. Time reversal operator is an anti-unitary and anti-linear operator. What I mean with anti-linear is that it follows this transformation. So if you apply the time reversal operator, it gives you the conjugate the conjugate and the state, the prime state. And it's also an anti-unitary because instead of preserving the inner product like here for the unitary operator, the anti-unitary t is actually given by this. This means that the inner product is the conjugate, not the original inner product. If you apply if you apply time reversal. So the time reversal operator is anti-unitary and can be written as a product of an operator k, not the meson, that converts states into their complex conjugates. So you have this one. This is the operator k, and a unitary operator u. This is this one. And so your time reversal operator is actually a product of a unitary operator and a k operator that gives you the complex conjugate. If the time reversal operator commutes with a Hamiltonian, this one, and if your psi satisfies the Schrödinger equation, this will also satisfy the Schrödinger equation. When, of course, t transform into a negative t, hence you have a time reversal operator. If the laws of physics are unchanged under time reversal, then they are a symmetry of the system. Now here is the Cpt theorem. So we know that charge conjugation and parity reversal are violated in the weak interaction. But according to this theorem, if charge conjugation, parity reversal, and time reversal are taken together, there is an exact symmetry so that the laws of physics are invariant. So this is the Cpt theorem. They should be together so that the law of physics still invariant. Colloquially, the theory means that if matter is replaced by antimatter, that is charge conjugation, momentum is reversed with spatial inversion, that is parity conjugation, and time is reversed, the result would be a universe indistinguishable from the one we live in. For the Cpt theorem to be valid, all three symmetries must be valid, or if one or more symmetries are violated, another symmetry would have to be violated to negate the first violation. So this is the Cpt theorem. In the weak interaction, there is Cp violation, and to compensate for the problem of Cp violation, there must be T violation as well. So this is also the Cpt theorem. In quantum field theory, in the context of quantum field theory, to satisfy special relativity, there must be Lorentz invariance, which means that Lorentz transformation is implemented this way. And the theory is the same. Now, quantum theory allows phi to be complex, which is, you can replace complex angle for phi, and your transformation would be this. So by setting your phi to be this one and then putting it into the transformation here, you will get this. And this one is a reverse time and a reverse space. So giving time reversal t, t transforming into negative, and space inversion x transforming into negative x, This is clearly a parity time invariant theory, and if the particles are charged, then Cpt invariance is recovered entirely, because if you have charge, you would have um, positive and negative particles. So Cpt is, invariance is recovered after Cpt in this case. So let me just read the summary. So quantum field theory in particle physics follows some discrete symmetries, and these symmetries are namely parity, charge conjugation, and time reversal. Interest in physics arises because these discrete symmetries are not conserved in weak interactions. The symmetry that is always conserved in all interactions is the Cpt symmetry, and this is of course the Cpt theorem. So that's it, guys, for this chapter, and so we're moving on to the next. I hope you learned something in this lecture.